Hello friends, welcome back for another machine learning project, network latency estimation using ridge regression. Before implementing network latency estimation using ridge regression, let's discuss what is ridge regression in Notepad. Ridge regression is a type of linear regression that includes L2 regularization. It is particularly useful when dealing with multicollinearity or when you want to prevent overfitting in your model. I have written that ridge regression is a type of linear regression that includes L2 regularization and also particularly useful when dealing with multicollinearity. So multicollinearity means nothing but the correlation between independent variables like x1, x2 to xn. Ridge regression is the extension of linear regression. So just we will apply L2 regularization to the linear regression, then it will convert to ridge regression. Therefore linear regression is a prerequisite, and I have explained in my previous video about linear regression. If you have any doubt, go and watch. Let's start with simple linear equations. So y equals to beta 0 plus beta 1 x plus some error, but as we don't have beta, so we will write b for that. So b0 plus b1 x plus e for error. Similarly, for multiple linear equation, we will have y equals to beta 1 x1 plus beta 0 plus beta 2 x2 plus dot 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 plus beta n xn and some error, that is e. In linear regression we use mean squared error. So mean squared error is the metric that we use to reduce the loss, and its formula is that y1 target minus y1 predicted whole square plus y2 target minus y2 predicted whole square up to yn target and yn predicted. This is the metric that we use for linear regression, and the same metric we will use for ridge regression also, but added some L2 regularization. The only difference between mean square error of linear regression and mean square error of ridge regression is that we will add L2 regularization to mean square error of linear regression. So that becomes now ridge regression. So let's write the formula for mean square error in ridge regression. So the mean square error of linear regression plus, let me write MSE for mean square error of linear regression plus lambda times beta 1 whole square plus beta 2 whole square plus dot 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 plus beta n whole square. So this is the mean square error of ridge regression. The L2 regularization is also called penalty, and it is proportional to the square of the magnitude of coefficients, and beta 0 to beta n are all called coefficients. So let's discuss on the penalty term lambda, and in some places it is also called alpha. So the lambda should always greater than 0, which is our regularization parameter, and this controls the strength of the penalty. After this, let's discuss some advantages and disadvantages. So advantages, the first advantage is that it reduces overfitting. So as it adds a penalty to large coefficients, which helps prevent the model from fitting noise in the training data. And the second advantage is that it handles multi-collinearity. So when features are highly correlated, ridge regression produces more stable and reliable coefficient estimates, which handles multi-collinearity. Let's discuss on the disadvantages of ridge regression. The first disadvantage of ridge regression is that it has no capability to select features, as when the coefficients are nearly equals to 0 or exactly 0, we should eliminate those features. That's why it makes less interpretable. And then the second disadvantage is that as the ridge regression is regularized, therefore it needs feature scaling. So this is also a step which requires feature scaling and for a better penalization, that may cause some disadvantages. And choosing a best lambda value also adds complexity to the model. And the last disadvantage is that the ridge regression also assumes the problem is of linear relationship. This is what the ridge regression is, which is nothing but a type of linear regression which includes L2 regularization. So let's move to the Kaggle notebook to implement the model. So let's go to Kaggle notebook. So we will estimate the network latency using the ridge model. First of all, we will import the libraries like pandas for data manipulation, numpy for numerical Python, matplotlib and seaborn for data visualization, joblib to shape the model, and we are importing train test split from the model selection of scikit-learn to split the data into train and test part. Then we are importing the ridge class from the linear model module of scikit-learn to build the ridge regression model. Then we are having column transformer from the compose module. This is used to pre-process all the columns simultaneously. Then we have a pipeline from the pipeline module to make a pipeline between the preprocessors and the final model. Then we have min max scaler and one hot encoder to do feature scaling and pre-processing. So these are the important required classes and libraries that we are going to use in our model. After this, we will prepare our data, we will load data. So this signal matrix.csv is available in Kaggle notebook. To add that data, click on the add input button, or if you have in local system you can also upload. So I have copied the path from the button, copy button, and having that path in the read CSV method to load the CSV file. So the read CSV method is from pandas, which will be loaded as a data frame in the df variable. After that, I am showing the first 3 rows using head method. So you can see we have different columns like time step, locality, latitude, longitude, signal strength, signal quality, data transmission, latency, network type, BB60 measurement, SRN run measurement, blade RFX A9 measurement. Among these columns, latency is our target column. After that, we will do some preparing steps, like we will drop some unwanted columns. As I thought the 2 columns time steps and locality won't be useful for our case, that's why I am dropping the 2 columns time step and locality. And if you want, you can go with the same data frame as it is. So to drop the column, we have drop method, and where I have passed the column names in the columns argument, and we have the argument in place equal to true, so that the original data frame will be modified. After that, to drop duplicates, we have drop duplicates method. So we are not checking whether the duplicates are available or not, but to drop it directly, if available, we are using the drop duplicates. And again we have argument in place equal to true to change the original data frame, and then ignore index equal to true, so that the indexes will be reordered. After that, we are dropping the null values if they are present. So to drop the null values, we have drop NA method. After that, we are going for information about the data frame. After the actions like dropping the columns, duplicates and nulls, we got this information where we have total 10 columns and total 16,829 rows, where the index starts from 0 to 16,828. So these are the names of columns and their non-null counts and their D types. So now you can see we have 9 float 64 D type columns and 1 object type column, that is network type. After that, we are plotting the network type column because it is only one column which is categorical column. So using the matplotlib and cbun and cbun's count plot method, we are plotting the column where we have passed 2 arguments. One is x for the name of the column, and another is data, that is from where the data is coming, that is from df, and then plt.show to show the plot. So here you can see we have 4 types of network type: 3G, 4G, LTE and 5G, and you can see the distribution of 3G, 4G, LTE and 5G are almost nearly equal. So after that we are just showing the first 3 rows of the data frame. Now you can see these are the first 3 rows after doing data preparation. After preparing the data, we will split the data into train part and test part. So to split, first of all we will take out the target column and also the variables or feature columns. So latency is our target column, so we are dropping the latency column from the data frame and saving that in X and taking the latency column only in Y. So after that we will go for data splitting. So using the train test split method and passing the features and the target, we will split the data into train set and test set. So here we have passed it to arguments test size equal to 0.2. That means 20% of the data will be reserved for test split or test data, and we have another argument random state equals to 42, so that whenever we rerun this cell or rerun this notebook, we will get the same result as now. So let's show the shapes of X train, Y train by shape attribute. So that should be of similar number of rows or same number of rows. So you can see we have same number of rows in both X train and Y train, while we have 9 features in X train. After splitting the data, we will pre-process the data. So to pre-process the data, we have the beautiful awesome class in scikit-learn, that is nothing but column transformer. So column transformer is a class which will pre-process all the columns or features available with us simultaneously. That's why we are using column transformer, and which takes 3 arguments. One is transformer, a list of tuples, then reminder which can be either a drop or pass through, then third argument is sparse threshold equal to 0. So transformer is list of tuples, reminders equal to pass through, drop for dropping the remaining features which are not mentioned in transformers, and if pass through is mentioned, that means it will pass the features which are also not mentioned. Then we have sparse threshold equal to 0. This will not allow the column transformer to generate sparse data. So when the sparse threshold equal to 0, that means no sparsity will be generated. After that we have only 2 preprocessor, one is min max scaler, another is one hot encoder. I have used min max scaler for all float data types, and for object data type, that is network type, I have used the one hot encoder. So you can see after running it, we got the column transformer. After that we will build our model. So to build our model, we are using the pipeline where we are passing steps. It is also a list of tuples. So the first tuple is a preprocessor and the second tuple is our ridge method. Preprocessor is nothing but our column transformer. So ridge method, when we want to know the default values in ridge, press shift tab. So you might be thinking about lambda or alpha that I told you at the beginning. So here you can see the alpha value is 1, which is also the lambda value. So that is the default alpha value and we are not going to change that. So you remember one setting, that whenever you want to know the default values, go to the cursor and place the cursor in the parenthesis and press shift and tab, so that you will get the default values. So let's run this model and see our pipeline. So let me run it. Now you can see at first we have a preprocessor, then our ridge model. So in preprocessor we have min max scaler, one hot encoder, then pass through. After that we have ridge. Then we will train our model with the fit method. So in fit method we are passing two things. One is xtrain data, another is ytrain data. So xtrain will contains 9 features and ytrain is our target. Through that it will train. So model is trained now by running that cell. After training we will evaluate our model, and I have written we will evaluate the model with the matrix MSC, which is incorrect. We will evaluate the model with the score method, and the score method is the default method given to each model. So in our case we will use accuracy, so we will pass xtest and ytest to the score method. And you might be thinking, where is error, where is beta 0, beta 1? Those are already calculated during training, and score method will only return us the accuracy of the model with the data xtest and ytest. So after running that, you can see we got 84% of accuracy we have with test data. So I have written a wrong sentence. Now I am changing that MSC to accuracy. Okay, after that we will save our model. So to save the model we have imported the library job_lib, and in the job_lib we have a method dump. Using that dump method we are passing the instance of the trained model and the file path where we want to save the model. So when we pass these two to the dump method, it will save our model. So after that we will save our cleaned data so that we can use it in during building of interface. So to save the data we will use 2CSV method. So as df is the cleaned data, we will save in a file name called network underscore latency underscore estimating underscore data dot csv. So it will save the data. So now we have saved both the model and the data. So to download these two models, go to the output section. In output section you will find a directory called output. So here is that output section, and that is the directory where we are working. Clicking on it we are getting two files. So click on the three dots and download both the files if you want. So with this we completed the first part. after building the model, now we will build the interface. So to build the interface we are using Streamlit. So let's import the required libraries like Streamlit, Pandas, NumPy and JobLib. Streamlit is for building the interface, Pandas is for data manipulation, NumPy is for numerical calculation and JobLib is for loading the model. So to load the model we are using JobLib, and make sure that you are having the paths as per the requirement, and I have downloaded the files in the same directory where app.py is located. So I am loading both model and data using read CSV method. So passing the file path name. After that I am creating the interface. First I have a container with 3 columns of different widths and 3 columns because to center the image, and under the second column I have an image method where I have passed the path of image and the width size. After that I have created a container for inputs. So as we have 9 features, so I have created 9 columns, but only 3 columns in each row. So we will have 3 rows and 3 columns so that 9 features can be adjusted in that area. So under the column 1 I am taking latitude with text input where user can enter a text, and here I have placeholder, that is enter latitude values, and the default value is minimum value of the latitude. If latitude is not entered then we will not do anything, and if entered then we are converting that to float 64 because all the latitude values were floating points when we built the model. So remember to convert the data type of the text that the user entered. Similarly for longitude we are again using text input and its minimum value is the default value, and the placeholder is enter longitude value. Again we are converting this to float 64. After that we have signal strength, and for signal strength I am changing the placeholder, and the placeholder value is the minimum value to the maximum value of that column or of that feature, so that user can understand we need to enter between that range only. After that the default value is same, that is the minimum value of that. Then I have repeated the same thing for signal quality, data throughput and other floating point columns, except one column, that is network type column. So network type column is a categorical column. So to select different types of networks I am using select box, where select box is such a widget where we need to pass options. So I am taking out the unique values of that column and passing as options in that select box. After that, as the previous floating point columns are how they are implemented, similar way I have implemented the BB60C measurement, SRS run measurement and Boulder FX9 measurement. and converting them to floating point 64 if they are entered, and having the same placeholder value, that is minimum to maximum, and the default value, that is minimum of each column to them. After that, I have a container for output. So in output, we need to provide the data to the model to predict yes or no. Yes, so I am creating a data frame for predicting. After creating the data, we will predict. So before that, understand how to create that data frame. So you need to provide the column names as keys, and the user enter values as list inside a dictionary. So that will be your data frame, and when we use that to predict, model will predict. And I'm showing with a success method the prediction, that is the latency in milliseconds. So let's run this in the terminal. So to open the terminal, we will press shift and tilt. That will open up our terminal. And remember that setting: to open the terminal, you need to press shift and tilt. And after opening the terminal, clean garbage if available, and if not, write streamlit run and the file name. In my case, it is app.py. If you have different file name, you can enter that. After that, press enter to run the Python file. So after pressing enter, you can see we got our interface, that is our model. So first we have an image showing some networks and latency. Then we have 9 columns, latitude, longitude to the last column. So with these default values, we have 120.03 millisecond as our latency. When we change these values, it will also change. So you can see now I will change. So when I remove the default value, it is showing the minimum to maximum value, and in case of latitude and longitude, it won't show because we have not used that minimum to maximum placeholder, but in other cases we have used. So let me enter some random values between minimum to maximum. So when we enter these random values, the latency is changing. So you can notice that latency, how it is changing and how I am entering the values. So I am taking a pause, but the video will continue. So thank you for watching patiently. Thanks a lot.